This is CPM Calculus Chapter 4, number 139. So here we're given three functions. F of x is sine of x squared, g of x is the square root of x minus 2, and h of x is 1 over x. So now we want to find the following functions and their domains. Okay, so these are all going to be composition of functions. So let's go ahead and do this. Part A. We see f. So we're going to go ahead and the composition is going to be f, and inside we're going to plug in the whole function g of x. So f of g of x is square root of x minus 2, right? And then we're going to plug this as the input to our function f. So f here is sine of x squared. So anywhere we see the x, we're going to replace it with the input. So here sine of x squared, but instead of x I have square root of x minus 2 squared, right, because it's x squared. And the square and the square root cancel out, so that gives me sine of x minus 2. Okay, so that is the definition of the function. But let's also now talk about the domain. Okay, so let's go ahead and see the domain. Well, remember, for composition of functions, the domain is restricted not only to the final function, but also to the composition, the input function, the composite function input to the other ones. So that is g of x here. And what we see with g of x is the square root of x minus 2. And we know that the domain is restricted to all real values. So that means inside the square root, x minus 2 cannot be negative. So it has to be greater than or equal to 0. Solving this inequality, we add 2 to both sides. We get x has to be greater than or equal to 2. All right? So our domain, right, if we continue on, sine of x minus 2 itself does not have any restriction, right? This is just going to be sine shifted right 2 units, okay? So this is just sine shifted right 2 minutes, but because it was the composite function, we have this criteria of our domain being restricted for x is greater than or equal to 2. So the domain is going to be 2 and to the right towards infinity. Okay, this is just set notation, and that's the domain. Let's go on to part B. Part B, we have two compositions happening. So let's go ahead and find the function. So this is just going to equal to f of g of, and plugging in h of x, which is 1 over x. So I'm plugging in the whole function, right? So that's what we do first. Next, we're going to plug in this as the input to our function g. So g of x is the square root of x minus 2. So let's go ahead and make that input to our function g x minus 2. So everywhere we see the x, we replace it with 1 over x. Okay, so that is the first step. The second step is to plug this now as the input into our function f. Right, so let's go ahead and plug this into our function f. So that's just sine again of x squared. And so that's going to be sine of our input, which is square root of 1 over x minus 2. And that's going to be squared. Okay, so simplifying that, we get sine of 1 over x minus 2. Right, because the square root and square cancel out. Alright, so that is the function defined, right? So let's box that. And then let's talk about the domain. So again, the domain is restricted not only to what we see in our final function, but it's restricted to the composite of every function inside. So h of x here, we know that the 1 over x, the denominator x, can never be 0 because that would make it undefined. So this says x cannot equal to 0, right? So this is, we're talking about domain. X cannot equal to 0, all right? Here, right, because this is again the composite here, this tells us a square root says that inside the square root, 1 over x, minus 2, since it's in the square root, has to be greater than or equal to 0, because if it's negative, it becomes imaginary, right? So let's go ahead and solve this inequality. Solving this inequality is a little tricky. We have to add 2 to both sides. We get 1 over x is greater than or equal to 2, right? Now what do we do? Well, since we have to look at 2 situations, okay? One is x being positive, what do we do? And one is x being negative. And we're going to see what the difference is by looking at both cases separately. So x is positive, I'm going to say if x is greater than 0, right? We're going to take 1 over x greater than or equal to 2 and multiply both sides by x, okay? Multiplying both sides by x cancels the x here, and we get 1 is greater than or equal to 2x, right? Divide both sides by 2, we get 1 over 2 is greater than or equal to x. We can write that in a different way. We could write that as x is less than or equal to 1/2, right? This is just writing this in a different way, in the other order, okay? So going back to the other case, if x is negative, so if x is less than 0, right, we start with 1 over x is greater than or equal to 2 above, but now we're assuming x is less than 0. Well, again, we want to multiply both sides by x. They cancel out here, we're left with 1, so we have 2x here on the right side. But since we multiplied the inequality by negative, we have to go ahead and swap the direction. So this is why we're going to consider both cases. Now we divide both sides by 2. We get 1/2 is less than or equal to x, right? And rewriting that the other way, we're going to have x is greater than or equal to 1/2. All right? Well, right here we see a contradiction, right? It says x is greater than 1/2. And also, our assumption was x is negative, right? X is less than 0, and x is greater than or equal to 1/2. Well, those can never happen at the same time. So this contradiction means this case does not provide us any values of x, right? So this means x cannot be less than 0, right? Contradiction. Therefore, x cannot be less than 0. So how do we write x cannot be less than 0? Cannot be less than 0 means x has to be greater than or equal to 0, right? So this case showed us, let's go ahead and box it in green. Over here we found x cannot equal to 0. Here we found x has to be less than 1/2. And here we found x has to be greater than or equal to 0, okay? Finally, we have the same thing here in our final function, sine of 1 over x minus 2. We have the fact that 1 over x cannot be 0 because we can't have 0 in the denominator, but that's taken care of already. So I'm going to go ahead and put an arrow there and bring it back up there, because we have these 3 requirements for our domain, right? X has to be greater than or equal to 0, and x has to be less than or equal to 1/2, and x has to be greater than or equal to 0. So we can use a quick number line to go ahead and justify our domain. So here is 0, right? Here I'm going to label 1/2, right? So these are our critical points. And I'm going to go ahead and shade in what can x be. Well, we know x cannot be 0, so I'm going to make that an open hole. X has to be less than 1/2, less than or equal, so I'm going to close it at 1/2, and it could go in the anywhere less than there, right? Except x here has to be greater than or equal to 0, so I'm going to erase everything less than 0. So these 3 things give us the restriction that x is between 0 and 1/2, and it can include 1/2 but excludes 0, right? So that gives us the domain. I'm going to go ahead and write it out now. The domain in set notation is just from 0 to 1/2, right? And we have a parentheses here because it's excluding 0, and a bracket here because it includes 1/2. Okay? So that is the domain for part B. Let's go on to part C. Part C, we have h of f of g of x. So this again is the composite of all three. So let's go ahead and do this problem. First, we have h on the outside and f on the outside. And the inside, we have square root of x minus 2, g of x. So this is now going to be replaced with square root of x minus 2. Now we're going to make this the input to the function f. So this f is here, sine of x squared. So that's going to be sine of the input, x square root of x minus 2 squared. Right? Let's simplify that. That's just h of, these cancel each other out, the square root and square. So that's sine of x minus 2. Now plugging h with the input of sine of x minus 2. Remember, h is just 1 over x. So that's going to be 1 over sine of x minus 2. Okay, so this is the final function. And now let's talk about the domain. Okay, so domain. So first of all, what's the restriction here? Well, this gives us the restriction that since it's in the square root, x minus 2 has to be greater than or equal to 0. Add 2 to both sides, so that means x has to be greater than or equal to 2. Right? Do we have a new restriction after we plug it into the function f? Well, we don't have any new restriction because sine of x minus 2 doesn't have any restriction. That's just the sine function shifted to the right 2 units. Finally, our final function is 1 over sine of x minus 2. So the only restriction here is that the denominator, sine of x minus 2, cannot equal to 0, right? That's our restriction. The denominator cannot equal to 0. So let's go ahead and find out when that's true. So let me quickly sketch just sine of x, right? This is sine of x. We know sine is 0, 0, and it goes up and down, oscillates forever in both directions. So here's pi, here's 2 pi, right? Here's 3 pi, here's 0, here's negative pi, and here is negative 2 pi. So sine of x minus 2, though, is shifted this entire graph 2 units to the right. So then I'm going to use a different color to go ahead and shift this 2 units to the right. So that's going to give us the point 0, 0. Pi we know is 3.14, so it's around 3. It's going to be something like this now. Right, so shifted to the right gives us this, right? Right, so in pink we have shifted to the right. Well, what are the places where sine of x minus 2 in pink is equal to 0? Here it's equal to 0, here it's equal to 0, here crosses the x-axis is equal to 0, here crosses the x-axis, here crosses the x-axis. So all these places are where sine of x equals to 0, right? And all that is, well, we started here and we shifted it 2 units to the right. So this right here, this point is x is equal to 0 plus 2. This point right here, it was pi, x was pi, and we added 2. This point right here, x was 2 pi, and added 2. So if you can see, we're just taking all multiples of pi, right? So x, when sine, I'm going to write it next to here. Whoa. Sine of x minus 2 equals to 0 when x equals to any multiple of pi. So I'm going to call that n times pi plus 2, right? Because we see we shifted it over, so we're adding 2 to all these values. So this is 0 pi plus 2. This is 1 pi plus 2. 2 pi plus 2. Everywhere it hits the x-axis is n pi plus 2, right? So saying that it cannot equal 0 means, therefore, x cannot equal to n pi plus 2, right? This is a new restriction because of this. Okay? So our two restrictions then on the domain, right? We have two restrictions. The domain is x has to be greater than or equal to 2. We have that right here, right? And x cannot equal to n pi plus 2. All right? So let's go ahead and write the domain just like this. All right? Because this is the domain of this function now. All right. So finally, let's go on to part D. Part D. We have h of x. So let's go ahead. This is a composite function. The input now is h of x. So the input is 1 over x, right? H of 1 over x means we have the input replaces x here. So it's 1 over x. And we know that's the same thing as 1 times the reciprocal of the denominator, which is x. So h of x, right, the composite function is equal to x, right? Well, what now is the domain? Well, our restriction here says that 1 over x, so x cannot equal to 0. The denominator cannot equal to 0. And we don't have any new restrictions. So our domain, right, we can either write it, we can say, there's many ways to write the domain. Right, we could write it just like this, x is not equal to 0, or we can write the domain in set notation here pretty easily, because it goes from negative infinity to 0 and starts again at 0 to positive infinity. Okay, so here's the domain for part D. All right, so that's going to end for us CPM Calculus, Chapter 4, number 139.